Hello, everyone, and welcome back to Index Office Hours. Today is the 13th of January, and this is Index Office Hours 239, marking the very first Index Office Hours of 2026. Happy New Year to everyone here. I hope you guys had a fantastic start to your year. I hope everyone is well rested from the holidays and is excited to have a kickstart the year with a amazing energy and have a fantastic 2026. So for anyone who is new to Index Office Hours, this is the town square where Graph ecosystem participants come together and discuss the most important and relevant topics for indexers. For the Just as a reminder, this is a conversation and we do love participation, so feel free to get involved in today's conversation via voice or text, and we will we'll get you set up. A bit rusty. Wow, I haven't done this in a couple of weeks. Very rusty, but here we go. As a reminder, this session is going to be recorded and posted onto public channels like YouTube. So if you are concerned about privacy, please bear that in mind. And with that, let's get into today's exciting agenda. As I normally do, I will hand off to Carlos for our regularly scheduled Repo Watch section.
Hello, everyone, and Happy New Year. I hope you had a quiet holidays, but I suspect the answer will be no if any of you is running Polygon, which is not news anymore, but it's still quite messy business. So we will start there. There have been several Polygon releases, that is from the forks, the Oregon fork maintained by Polygon. We are now at 3.3.6. This also includes a hard fork for the past day 9, so you're probably running that or your chain should be stalled. Along the way, since the last IOH, because it's been a couple of weeks, there were some previous versions with hotfixes and the usual Polygon churn, but we are now, in terms of Oregon, at 3.3.6 and supposedly working well until the next hotfix. On 𝗨𝗀𝗪 v2, we also bumped a few patch versions, and it's now at 0.5.5, so you should pair that one with the Polygon Oregon, and it should be working for today. Accompanying those Polygon releases, we have also from Streaming Fest a few releases from Go Ethereum Polygon Fork, so that version is now at 2.5.6. There's also been a churn of a few ones since last IOH, but this is the latest one and is up to date with Polygon. Now that we're in Streaming Fest, there's also a Firehose Ethereum new version. There's actually been released 2 since last IOH, 2.14. something, and now the latest one, which is another minor bump, which is 2.15.5. So among those two, there have been a few future editions. You can check the change logs. I only have on the agenda for the latest one, but bear in mind that there's also been a previous one since last IOH. So that covers Polygon and the Streaming Fest releases. Next, we have an Arbitrum Nitro release. This is very recent. I think it's from the 7th, a few days ago. It's a patch version. It's not critical, not very urgent to update unless you run validators with batch blobs, which I think most of you will not, but still may include some extra small fixes. And it's been a while since there's been a patch release for Nitro, so we're now at 3.9.5. There's been an Avalanche release, 1.14.1. The changelog does say it has significant changes, even though it's just a patch bump. So bear that in mind if you're running Avalanche. There's a new version, and don't be fooled by the patch version. Seems to pack quite a lot of changes. There's been a new miner for Nethermind. We're now at 1.36.0. If you're running Nethermind, beware that this miner version has configuration format changes, deprecates a bunch of options that have been phasing out and will now not work. So upgrade carefully if you upgrade to this Nethermind version. And regarding execution layer clients, I think we got them all. Let me just double check. Yes. On the consensus client, there's two releases to report. There's actually a couple of patch versions for Prism. It's now at 7.1.2. The previous one to this one, which was missed since last IOH, 7.1.1, did have a critical fix. So if you haven't updated yet, you probably want to, then you can jump right to the latest one. And there's a new Nimbus release. We're now at 25.12.0, which is a minor bump since last one. On the graph stack, there's only a new tap agent. We're now at 1.12.3. Minor improvement, it's not very urgent. And no new charts yet. They should be coming out throughout this week to update Nitro and these new releases, which have not been actually that varies outside of the Polygon chaos. So that's it for this last couple of weeks. And I'm handing off to Huawei as usual for Protocol Watch.
Thanks, Carlos. Okay, I think I have my audio settings quite changed, but I think you can all hear me okay?
Yeah, loud and clear.
Okay, great. So there's not a lot to update on Protocol Watch aside from contract repository. So forum governance, forum research, and the network subgraphs are all with no new updates since the last IOH, which has been quite a while, but also makes sense given that it was the holidays for the most part. On their contract repository, there have been a lot of updates on the rewards eligibility oracle, particularly the issuance allocator, as well as many other PRs. The full list of all of the PRs is available in the agenda if you're interested in any particular one of those. But the TLDR is that, again, there's a lot of updates on the rewards eligibility oracle, some audit and fixes to the issuance allocator, and some dependency updates as a chore. And that's pretty much it for Protocol Watch. So I don't know if Kate's around. I don't see. Should someone else take Project Watch? I'm not entirely sure.
We're skipping.
Okay.
We're skipping. So don't worry about it. And no worries about it, Carlos. No agenda swapping around. No derailing of the agenda. That's fine. Okay, fantastic. Now I will hand over to Rem, who's going to take us into a presentation on AMP in the graph network.
Yes, hello. It's been a while since I've spoken here, and it's actually quite an exciting topic to be here about. So I think everyone's going to be very interested in this. We've been working on AMP. You've probably heard a little bit about it. Ford's actually going to go into a little bit more of the detail on that. I'll just advance the slide actually. And then I'm also going to talk, and Samuel's also going to talk a little bit about the network side. So basically, I'm about to hand over to Ford. Ford's going to spend a little bit of time talking about AMP, which is the blockchain native database, which we're going to use for this new data service on the graph, which is actually, I think, going to unlock a huge amount of new potential for the graph. And then afterwards, I'll come back and I'll talk a little bit about the AMP network, about how indexing works on it, and Samuel's going to then speak about indexer selection and service pricing. Now, before I do hand over to Ford, are there any particular questions that already arise from that rough agenda that you'd like us to focus on or talk about? And if I get no answers to that, I'll presume the answer is no. And Ford, are you ready to take over and show us AMP?
Yes, I believe so. Can you hear me?
I can indeed.
Cool, loud and clear.
All right. Perfect. I'm on a new machine. You guys know how audio can be tough with Discord, so glad that's working. We're off to a good start. I'm going to now share my screen, and it doesn't look like I have permissions for that. Bear with me here. Uh-oh.
Able should form.
I'm actually having trouble sharing my screen here. Do you guys have a incantation I can do here? Settings I can change?
Okay, so first of all, let me try and see if you have the necessary roles. If not, then what I can do is you can, yeah, okay, you should be able to, you have all the necessary permissions. What you can do is you can shoot over one of whatever you want to share to me on Slack or on Discord DMs or whatever you prefer, and now I can share it.
Maybe I'll just have Rem share his screen because he's
Okay,
already
cool.
sharing.
Yeah, sounds good.
And you may not have permissions for this slide deck. So I
Okay.
just sent you a DM, Rem, with the slide deck.
Sure. I'll just pick that up in a second and start that.
So yeah, I guess I'll just let you know when we go to the next slide if it's not obvious, and you can be my clicker.
Looking forward to it. Yes. Yeah.
Yeah, so just let me know once that's up. I can't.
Hopefully you can see it.
Yeah, it's loaded for
Good to see
me.
it.
Cool. All right, so I'm assuming most people here are already familiar, at least with the context that we're working within, which is within the challenges of blockchain data, and maybe have some context on AMP, but have getting information filtered in from different avenues. And so I'll assume that no one has context on AMP here, and I'll do a quick intro at a high level. I will try to speed run through this high level deck pretty quickly so that we can get to more technical in the weeds things and get to your guys' questions, as well as Rem's and Samuel's section of this presentation. But please ask questions as I go, and I'm happy to stop and discuss things. So first I'm going to give like the high level overview kind of from a user perspective, and then I'm going to jump into some architecture diagrams and look at like the operation side of things, because I know that's where you guys think about things. So if we go to the next slide, Room. As I'm sure I don't have to tell you guys, blockchain data is not easy. Blockchains generally don't expose a really good, clean read primitive. Blocks can be replaced, chain history can reorganize, state needs to be decoded and reconstructed from raw binary data. I could keep going on and on about the challenges. But users still have the same strict requirements. They need low latency, high quality data. They need accurate data. And they still have those expectations. So we need to try to figure out how to bind those two worlds together. Yeah, next slide. Okay, cool, you're on it. Many solutions are already being built for blockchain data, but they tend to take already well-established technologies and restructure them and try to put them together into complicated data pipelines to make it work. Most of the traditional data processing technologies really weren't designed for blockchain data, and so we're having to add a lot of tooling around them or force ways to restructure the data, reorganize the data to handle the requirements of blockchains. And generally, all this plumbing trades the complexity of the problem for an ever increasing complexity in the systems that we build. And so we realized that we needed a purpose-built solution to solve all these blockchain data needs. It used to be a pretty well-known fact that building a database from scratch was not really feasible for a small team. It was an enormous feat. It required deep pockets, a huge team of engineers, and really years to pull off. But things have changed, and now is the time where modern modular databases can be built from open source components. And our team has come to enough collective understanding of the problem and the domain and an understanding of these modern tools that we just thought the time was right to really build a purpose-built blockchain database. And so with that, I introduce to you guys AMP. AMP is our take on building a database specifically for blockchain data. It provides high throughput batch query capabilities as well as low latency streaming. AMP speaks standard SQL for queries, streams, and transformations. So it's familiar interface for analysts, developers, as well as like agents and LLMs. All right. So with the design of AMP, we're bringing together two amazing software ecosystems and larger ecosystems. So powering decentralized networks and applications using innovative blockchain systems, as well as learning from all the traditional data systems we've seen today. So we are combining those together, and we're using what is known generally as the FDAP data stack to build a custom database for blockchain data. So in particular, what this means is we're building on a few important pillars, open source software, Apache Data Fusion and Apache Arrow are big pieces of that. So Data Fusion, you should be able to see the logos here on the screen. Data Fusion is a portable and extensible query engine, and it has leading performance compared to even closed source databases. And this allows us to build a database around this query engine. And Arrow is a column-oriented in-memory data format that supports zero-copy reads and fast interchange between many different programming languages. It has a lot of cool tools. I could talk about Arrow for a while, but it's a very efficient in-memory format. And we're building on those as well as the Parquet data format for file storage. Okay, next slide, Rob. And so, yeah, just to kind of repeat on that point, like we're learning from what we've built in the past, and we're really building on standards now. And so building with these open source standards allows us to plug into really already vibrant ecosystems of developers and of tooling. So Arrow, Apache Arrow and Apache Flight already have support across most languages. And there's all sorts of tooling built around it already. Really cool stuff. And then there's the Arrow Database Connectivity Standard, also known as ADBC, that allows us to create custom drivers for connecting standard BI tools and other data viewing and managing tools on top of our database. And then the Apache Arrow ecosystem has many SDKs and many supported connectors for loading data into different data systems. It supports applied SQL queries directly to the in-memory data. And there's all sorts of machine learning libraries, et cetera, built around this and data science toolkits. So by building with these standards, we allow you guys and our users to plug into this existing flourishing ecosystem. We also really wanted to make this something that is a tool that's very applicable at different levels of the stack. So as a developer, it's really easy to just run on your machine and test things. As an indexer, it scales easily. It's very clear how to run it. You can run AMP from a single Rust binary. You can run it in a more distributed setup. And so, yeah, run locally, scale globally. Another important part of that story is the smart contract development story. I won't get too into detail into that, but essentially you can automatically have data sets built for you as you develop your smart contract locally. So why SQL? Declarative SQL allows you as the user to define the what that you need and not the how. And so that allows AMP and our development team to optimize how things are done under the hood, optimize the plans, change how queries are executed, improve parallelization without you ever changing your behavior as a user. You focus on the what, and we focus how to give it to you in the fastest way possible. So SQL is really powerful. It's also self-documenting and expressive. So a SQL statement can say a lot about your business logic and can communicate more than just your data needs. And also coding agents really love SQL and are great with it. So that's a pretty nice bonus. Here's like a really pretty simple example of a streaming SQL query. So you can see here, we're just selecting data from the logs table of Ethereum mainnet, filtering on an address, and then setting streaming equals true. And so what will happen here is the query will first process all the batch historical data that matches that filter, return it to you, and then continue to stream data to you as new blocks are mined, as well as handle reorgs and sending change requests to you when reorgs happen. So you can see, like, you can write simple SQL, you can understand, and it's very similar to batch SQL, and easily get streaming primitives from that. AMP also provides flexible compute over your data using user-defined functions. So for computations which are cumbersome to express directly in SQL, you can declare and run UDFs that define, it could be arbitrary logic. We also provide a nice set of out-of-the-box UDF utilities for users. For common blockchain operations, we have functions for decoding data using ABIs, functions for formatting binary data, converting hex data to strings, decoding params like you see here, et cetera, a bunch of useful functions, and these can be easily parallelized by the query execution engine across many rows. So with the things we have out of the box, plus the ability to define your own UDFs, anything's really possible. And then if you need the data more than once, we have the concept of AMP datasets. AMP can materialize your data transforms into dataset tables, and then those can be queried directly or further composed into higher level transformations and reused and composed to create other datasets. So these are basically like materialized SQL queries. The datasets can be versioned and then uploaded to a registry. And then they can be continuously streamed and materialized into the physical tables. And so this is like what a registry might look like. This is a proof of concept that we created and we open source or released and had users have access to it, the Buenos Aires Dev Connect. You can see here we have data sets, we have raw data sets, we have derived data sets. Users could create their own and deploy them to this registry, as well as use data sets from other users. So yeah, we opened this up for the hackathon participants and had some great hackathon projects built with this. And they were able to upload their data sets and reuse them in Power Applications. Of course, a huge note here, this is a big work in progress. This is a beta application here. And okay, yeah, we can go to the next slide here. So how can that data be consumed though? Of course, you guys all understand SQL queries and we can have tools that send SQL, but we've also created a few libraries for interacting with the AMP system. So we have libraries in Rust, Python, and TypeScript at the moment. And here on the screen is an example of using the Rust client, which provides a durable streaming client on top of our reorg-aware SQL streaming. So the server doesn't have to hold any state in the system. This is all stored on the client. And that's really great for scalability and operational efficiency. Streaming in this case is durable. It can be easily recovered and resumed from checkpoints in case there's any failure scenarios or network issues. It also comes with transactional guarantees and exactly once semantics, so you know you're only getting your data sent into your destination store once. Here's an example of building on top of that core Rust streaming client to do CDC, change data capture. You can see here in this match statement that if you understand Rust, it's fairly simple here to take the next item in the stream and figure out, is this an insert or a delete, and then take action based on that. So building on top of the standards we've created is pretty natural and efficient. We've done a pretty complicated thing here in just a few lines of code. What about performance? That's going to be a question everyone asks. That's important. What do we got here? So AMP is pretty performant. We're able to keep up with high frequency chains, pretty low latency at chain head, around 100 milliseconds on average. And then next slide. AMP can decode lots of events pretty quickly. We can load and decode millions of events per second. We benchmarked this with Uniswap swap events. And this number here was from that test. We were able to do around 4 million events per second in this real world test, processing raw blockchain logs with this query here. So this is the query that's decoding swap events. Yeah, no questions on that. We can go to the next one. Another benchmark is querying all the block hashes on Ethereum mainnet since Genesis. It takes about 5 seconds. Crunching all transactions since Genesis, about 35 seconds. And this query here has a little bit of complexity in it, and it is splitting the transactions into 2 groups and counting them. So it's not just returning all the transactions, it's actually aggregating across all of them in less than a minute. All right, so that was a lot of like the kind of user-facing high-level overview. And now let's jump into how some of the stuff works under the hood. So here we have one way of looking at the AMP architecture. And this is kind of focused a little bit on the data flow. So you can see starting from the green box on the left here, we have the blockchain data sourced from RPC or tracing mechanisms in the blockchain node. And then that is feeding into the AMP node via the AMP extractors. The extractors are built into the AMP binary, and they are constantly pulling those data sources, importing the data, and then writing the raw files using the table writer. That's writing Parquet files to object storage, which you can see in the box at the bottom there, the storage layer. And that is also adding entries to the metadata DB, which is a Postgres database, which keeps track of file statistics, where all the files live, what data is in each file, and that feeds into the query execution engine. And so when the query execution engine is executing a user query, it's able to query the metadata DB to understand where all the files are, what data is in each file, and what it needs to access in order to process that query. And then it comes up with a query plan, pulls the files in, scans them as needed, merges them, joins them, does the operations it needs to do, and then it's able to return that to the user using that query server and the Aeroflight SQL protocol, which is a gRPC binary flight protocol. And this might be a good time to stop and answer any questions as we're getting into the detail here of how things look under the hood. Does anyone have anything about how that works before I move on to this diagram here?
I see Vince is typing, so let's just have a look at the chat. And yeah, folks, you can either type or feel free to hop on the mic, wherever is easiest.
So as Vince types that, let's see, what does the PG database contain? Yeah, so the Postgres database, as I mentioned, is as the metadata DB. So that will contain things like locations of all the files. So for a particular data set, you might have multiple tables per data set, and each table will have likely many files that represents it. So the metadata DB has the mapping for all those. So which tables are in which data set, which files represent each table. For each file, what block ranges does that file have, as well as many other statistics that feed into the query execution engine, so it knows which files it needs to access. A really important aspect of that is not accessing too many files and trying to be efficient there. This stuff is open source, so I can share a spec of everything in the metadata DB. That's kind of the high-level important stuff. Maybe go back to that last slide for a minute, Ram, and I can talk about that. This is a little bit more of an architecture diagram from an ops perspective of which deployments you would have in the overall AMP deployment, AMP server. So it can be run as a single binary. By the way, ampup.sh is where you can find all the installation instructions and tools for pulling down that single binary. So you can run it as one binary, and then You can also run it in a more distributed scalable setup like I'm showing here. So here we have an AMP server deployment, AMP controller deployment, 2 AMP workers, Postgres database, and the object storage. The AMP server processes queries. The AMP controller serves up the admin API where you can interact with it to list jobs, create jobs, stop jobs, get information about workers, etc. All these admin interfaces. And then the AMP worker is what's doing the work of populating the data. So like creating the data sets, extracting the data, compacting files into bigger files. And then the data stored in the object storage and the metadata and coordination data is in the Postgres DB. And so as an indexer, this might be the deployments you have on your AMP system. And that's pretty much what I have. I think the next slide just has a few links to our repositories and to ampup.sh. And that is kind of the AMP database core. And the next sections we have are around how we might run AMP on the network and integrate it with the protocol.
Any questions on that part?
Yeah, as I said, guys, feel free to either type in the chat or come on the mic. I see that Mark Andre's typing, so I'm assuming questions coming.
No questions can be good. So yeah, we may move on to Rem. And if you guys think of any questions, feel free to shoot. Yeah, I'll be around. Go ahead.
Let me just quickly share the switch back. Okay, so you just heard about AMP. What's referred to here as the blockchain native database, right? And really today's session is actually, from my perspective, focused a lot on sharing. Okay, so how do we make that work on the network? And I will say we're at quite an early stage here. So we are very much looking for feedback. All of your observations, all the input you give, etc., will definitely help us shape exactly how we make this work on the network and how we bring this to market. I think it's a very exciting proposition, but there are still definitely also a lot of questions that we want to work out on the details. So I'm going to start talking about AMP indexing before handing over to Samuel, who's going to talk about the indexer selection part. So AMP indexing. I'm actually going to break this down into 3 parts. So one, I'm going to talk about the indexing agreements. Then I'm actually going to talk about this last, actually, the indexing subsidy that allows all of this to happen. And I will talk about the indexing payments, how indexers actually get paid for the indexing work we do. So if you look at the indexing agreement side, and I have very much tried to bring these down to just the basics. There's actually quite a lot of detail in each of these steps, but so you can see the overall perspective. We select indexes based on price, stake, quality of service, and Samuel's actually going to go a little bit deeper into how that works, what all the criteria are. And then send signed index agreement vouchers. Any AMP indexer then can decide that they want to accept that agreement. We hope that it becomes the norm that indexers do accept agreements that are offered to them. And they post the agreement. They'll also provision for that, and they'll call start service, which means they are now, they've bound to an indexing agreement, which can give them a source of revenue for indexing that data set. And then periodically, over a period of time, they will submit their proof of indexing and collect fees. And I'm going to, that loop part, I'm going to expand on the next slide, because that's actually where you see the payment flow. So I'll just pause there briefly. I think so far we do have a couple of people. Okay, so that's Ford's just shared some great links, and I would encourage you to all have a look and play around with that. We want to understand from you how you find the experience, what we still need to do to get it to the network as quickly as possible. And I see Mark is typing something, but I'm going to move on to the next slide. Okay, sorry, here's a quiz. Please take some time trying it out and providing feedback. All right. Actually, that. So the payments side of the equation. I'm not sure how many of you have watched closely the details of how, you probably have, how Horizon was different from the protocol we had before, right? So one of the important differences is that instead of an allocation being closed and reopened, they are long running, and you can keep collecting, and that works quite well with the way AMP indexing works. So you can keep it open, and periodically, this can be every epoch, it can be less frequently if you want, but I suggest typically every epoch probably makes sense. You submit the proof of indexing, and you can, provided it's within the right parameters for the indexing agreement, you can collect the fees for that. The AMP data service essentially requests that payment be made from the AMP subsidy, and this is a slight simplification, but essentially you get the GRT transferred back to you. And I see there's a question now from 𝗨𝗂𝗂𝗧. So are we envisaging having multiple gateways like we have on the subgraph networks? And the answer to that is yes, absolutely. I think from my perspective, I don't actually want long-term necessarily edge node to be the dominant gateway, but I think practically in the early stages, while we work on supporting and building the network, I think edge node will be a dominant gateway. How quickly that changes, I don't know, but it's probably also linked to how quickly the network grows, and therefore there is demand and need for that. Hopefully that answers your question. Okay. Now, the last bit I was going to talk about is just briefly mentioning the subsidy. So you're probably aware at the moment, all of the issuance goes to indexing rewards. I'll classifying them as subgraph rewards here. We're going to take a slice of that, I think maybe 5 to 10%, and read and direct that to being able to subsidize activity on the AMP network. And I say 5 to 10%, by the way, because I think over time the network should become self-balancing, and we want to put in mechanisms that allow the network to self-balance rather than us making specific governance decision about how much goes to one data service or another. But this, I think, allows us enough space to get this data service working properly and the network working properly, as we also build those mechanisms that makes the network self-balancing in the long term. And I see there are more questions coming up. I'll pause there briefly, but I'll also mention, Samuel, have you been able to get your audio working? I can't hear you.
Yeah, if you can hear me, then it's working.
Yes, I can.
Oh, no. Can you hear me? You can't hear me?
Yes.
Yes, loud and clear.
Yeah, we can hear you. So,
Okay, cool.
So in addition to network subsidy, is the gateway going to be paying the equivalent of DIPS? So basically, the network subsidy is what is paying those indexing agreements, those DIPs, if you like. I tend to avoid the word DIPs and just say indexing agreements, but what we're essentially talking about the same thing. Okay, I am going to let Samuel introduce his part.
Okay, great. So yeah, we're gonna look at the selection part of things with regards to AMP. As we look at selection, kind of two components here. One is which indexes being asked to serve the data set and being paid accordingly. And then the other component is the query time component. It's very similar to how the subgraph data service works, and how DIPS in the future for the subgraph service should work. So the query time selection is kind of handled by a more high performance selection algorithm that should be running in real time and routing queries or sending queries to the indexer that is most best prepared to handle that query in order to sort of optimize for latency. Whereas for indexer selection for the data set, we're kind of more focused on kind of making long-term agreements, and that selection doesn't necessarily need to happen at the kind of latencies that we're dealing with query selection. So we could probably just advance the slide a little bit.
Do you want the next bit as well?
Cool. Yeah, sounds good. So yeah, with regards to the dataset component of selection, there's various factors that we're going to be using to rank indexes and determine which indexer is best positioned to take on that AMP indexing agreement. So some of these components are the same as what have been proposed in the subgraph DIPS side of things. So for example, stake to fees ratio, which the kind of benefit of there is to prevent identity splitting. So kind of protects the network against those Sybil attacks, where an indexer with a large stake might prefer to split their stake across multiple nodes. So that kind of component is to prevent that and to make it so that there shouldn't be such an incentive to do so. We also have a price component, which is actually made up of various other factors. So I think there's 5 factors that go into price, and we can come to that in a second. We have a latency component, and the benefit of including that is just to incentivize the best latency and then to ensure that consumers are getting the best latency from the product. And then just to run through the other ones, we also have uptime, POI, so our index is submitting the correct data. And also there's kind of like a final component here, which is work accuracy. So as it's proposed at the minute, with regards to AMP, index is actually going to be submitting to the gateway to tell the gateway how much work they have done. And there is an opportunity there for, well, I say opportunity, but it's not intended as an opportunity. That indexers could artificially inflate the amount of work that they've done. So what we're trying to do here is to ensure that work is reported accurately, and that's why this goes into one of the selection criteria. So yeah, we could probably go to the next slide. Okay, so on the pricing side of things, we break down pricing into multiple components. So one is a indexing time component, and the other is a query time component. So indexers will be able to charge based on various factors, and how much they decide to charge is obviously up to the indexer, and they're able to state their specific prices. So, for example, one of the components here is a price for how much gigabytes that you're storing, and if, for example, you have high overheads, then you might want to have a higher price per gigabyte stored to make sure that you're being compensated effectively. But obviously, the lower that you charge, the more indexing agreements that you could be likely to receive, because you'll be prioritized more by the selection algorithm. And just to cover that point on the screen now, we would also have a price per RPC query. So as you're syncing the AMP datasets, you're querying your RPC node millions of times, and then you're making sure that you're being compensated for that. And then at query time, there's also pricing that goes into selection there. So we have a price